based on the work that already exists from the Kaggle dataset, the Kaggle, notebooks that are already available. So the idea is to just discuss them a little bit. Like what we try to do is to kind of like make a mix of or a summary of what we have over there, so we can discuss. And this is of course like something on construction. We'll probably share on Kaggle as well. So you'll have this information there. Like it's still a little bit messy on my side because I didn't have much time to prepare. But then we can, of course, like later on, I will upload probably in the next days, and you can check it out as well. So let me just get started over here. And of course, if you have any questions, feel free to ask. The idea is to be something that is very conversational, so we can all like take the best out of this session. Can you guys confirm you can see my screen?
Yes, it's visible.
Okay, good. Thanks. And yeah, as I said, like if you want, you can ask questions on the chat. I'm sharing my whole screen, so I have to go to the meeting, to the Google Meet to see. But or also like Aaron can also like help with answering some of them and so on. But it's good that we keep the conversation going. So for the initial part of the session, then the idea is to have like a deeper look into the data set that we have so far. And as I said, like we're going to be doing some preparation and some initial exploratory analysis, and then look into the features, and also a little bit about the preprocessing steps. And then after that, Aaron will take over and discuss a little bit about the modeling and the submission and so on. So here in this initial part, it's just like some libraries to import. Like here, I'm not even like using all of them. I was just like trying to make a mix of everything. But mostly we're going to be using, of course, like a pandas because we're going to be transforming our data set into a pandas data frame. We're going to be using Matplotlib or Seaborn for some visualizations. We might also use some like stats and like also NumPy as well. And most importantly, we're going to be discussing today a lot of sklearn steps, such as for feature engineering or preprocessing, and also for later on for the models as well. So here are just a couple of them. As I said, I will share later on this book as well, so you guys can have a look. So here I am downloading the data, or I'm reading the data already from my local file, my local computer. If you are using Colab, you have to first put it in or access it from your drive and so on. But I think for the way we are going to be working here, we're going to be using Jupyter. I don't know if Aaron is going to be using Jupyter or Colab, but we'll see. So, but basically we have the train test data sets. So we are reading from a CSV file. This is the format that they have. And we are transforming them into a pandas data frame. So this is basically what we're doing here. This PD is the pandas data frame. That is what we have, how we are importing here. So I guess you guys are all familiar with this, but just in case. So the typical steps for like looking into your data, you look into like you can just like do an info to just see what are the columns that you have over there, what is the type of your data, what are the number of non-null columns that you have, and so on. So here, for that, just paying attention that we start with 0. This is very typical for. Oh, sorry about that. This is my translator. This is usually like how Python counts. So you can see that we have a total of 74 because it's 0 plus 73 columns. So these are except by 1, that is our target value. These are all our features. So we have 63 features originally on the raw data, so to say. And you can see that in most of the cases, we have a total, or you can even see it here, we have a total of 757 entries for the training data set. This is very important. We are looking into the training data set. The test data set is much smaller, it's like around 9,000 something. But just so you guys have the initial look into the data. That's the idea. And then you can see that we have like some types are integers, sometimes they're objects, sometimes they're floats, and so on. We're going to go through this as well. But this is basically like the first initial things that we can see in our data set. So You can see that each building has 64 features. You can see that there is an ID for each of the buildings. That is like what identifies the building. And we can also infer, if you pay a little bit of attention to some of the names here of the variables. For example, we have here precipitation inches, snowfall inches, and so on. So we can see that this is probably the unit of the variable. Same here for, sorry, where was I here? So the days below 30 or Fahrenheit, or days above 80 Fahrenheit, this is temperature, and this is in Fahrenheit. So mentioning this because Fahrenheit is a very common unit in the United States, not much in necessarily other areas of the world. So, for example, here in Europe and at least in Brazil, where I'm from, we use Celsius. So just something to be aware of, because you might have to like just think in terms of those units as well. But so yeah, this is the first glimpse of the data. Now, if we look a bit closer to all the 63 columns, we can see that some information are more like about the buildings themselves, like the year factor, the facility type, the floor area, and so there's like a very specific information about the building, also elevation, like the elevation of the location where the building is, and so on. You also see that like you have minimum, average, and maximum temperatures, temperature for all the months of the year. So we have this 3 times 12. So we have like 36 variables that are specifically about monthly temperatures, like related to monthly temperatures. And then here at the end, you have something that is more like a weather information, like cooling degrees, days, and the average temperature and days below some specific temperature. So this is, you see, like this is more like a weather, whereas this is more like a monthly temperatures. So if you want, just for the sake of making your life easier to understand, you can consider like just for the sake of organization and so on, divide a little bit of this features into different categories, like just how you're going to be interpreting them. So for example, here I put like building characteristics, like the ID, the year and state factors, building class, facility type, year built, and so on. Then the month temperature info is basically all those 3 informations, min, average, and max for all the months. Then the general weather information. So this is basically what you have. And important, you have your target variable, that is this site EUI. I'll discuss a little bit more about the specific features a little bit further. But another thing that we can do, like once we understand that there is like because if you look like there's 64 or 63 features, this kind of stuff, you're like, oh my God, like how am I going to make sense out of all of this? But if you try to see that there are some similarities, there are some features that are about something, or they all have more or less the same unit, it already helps you to have a notion of that they are all about the topic and so on. So it makes it easier for us to understand what we're going to be doing in the analysis as well. And of course, like how we're going to be handling those features. So if we look into missing values, I mean, there are like lots of those notebooks out there that do like some very nice things, like with percentages and so on. So you just have to look into some of them. Here I'm just showing like the values, like if you would just want to know, this is a very nice thing that you can do, that you can just do is null and then just sum, and then you can get all the NaN values that you have in your data set for a specific column. So here you can see that for the training and the testing, the test data sets, so here the test data set starts, so sorry, this was the train data set, and then here in white is the test. And then you can see that more or less the same variables have missing values. The others don't have any missing values, which is great, which is usually not the reality in the real world. But yeah, so we have those features here that have some missing values, and we will have to make a decision of how we're going to address those missing values. And By missing values, I mean like there is a building with an ID that doesn't have the year in which it was built, or that doesn't have the direction, peak, wind speed, and so on. So if you look in terms of percentages, we can see that for the training data set, only 2% of the year built is missing. So that's not much because we had, like, if you guys remember, quite a lot, like 75,000 and so on. So this is not really much. Here is something around that. Apologies, there is some mistake here, but it's also something that is very negligible. That means that we can find ways to deal with the missing values, but we don't need to necessarily like discard the variables. So for the Energy Star rating, we still have quite a bit of missing values. For the training set, we have 35% of missing values, and for the test data set, we have 23% missing. But this is still like something that is a small portion of the data, and it's not something that is like half of the data. So like it's something that we can still keep. We'll just have to see like what is the best way to deal with that. So for other variables here, especially for the training data set, sorry, for the test data set, you see that all the direction variables about wind speed, and also basically all the wind variables, like also the maximum wind speed, direction, and also the days with fog have quite a lot of missing values. They have, like, for the training around 60%, for test even more. So it doesn't make sense for us to use those variables because they will just bring a lot of uncertainty to our model, because we don't really know those values, and we will have to, if we keep those values, we have to find a way, and this is going to be a way that is not very consistent because we don't have so much information about them. Even if we want to take an average, we cannot take much of an average because we have only, like, in some cases, like only 10% of the data, or almost a bit more than 10%. So this would basically bring noise to our data. That's why we're not going to be using them. So the strategy with those 4 here is going to be to drop them. And whereas the others, we can still, like, think of ways to deal with them. So this is one important step, like deciding what to do with variables. So we know that out of those 63, there are 4 that are already out, and of course, like the ID as well, because the ID doesn't bring any information. It's good for us at the beginning just to have this information, just to know which building we're talking about, especially when we're not doing this here in this project, where we are like collecting data and so on. If you want to review, then it's nice to know the ID. But once this part of the pipeline is done, like then we don't need it anymore. So in this case, you're going to have now, I think, 58 variables to deal with. So, or 57 maybe. So this is one step. Now we can look into the data set, like now that we already saw this, like we were just looking at the columns, remember, and just looking at the missing values and so on. And we already made quite a lot of important decisions, like that we don't need to use some of them. Before I continue, I don't know if there is any question or comment. I'll just go quickly here to check if everything's fine.
I'll take care of questions, Rosanna, so you can move forward.
Okay. So yeah, so just looking to the data set, we have here just like looking to the header of the data set, like just the first 20 lines. You can see all the, I mean, you cannot really see all the variables because the Jupyter Notebook will not show all of them, but you can see several of them. This is just like to have a feeling of how they look like and so on. So then here, for example, that you can see that there are some days that have those not a number, but this is one of the variables that we decided to drop. But there will be, of course, other variables that we are not dropping that will have those not a number, and we will have to address this. So this is something important for us to remember. But yeah, this is how the training data set looks like. And we can also look into the test data set. It looks quite similar, smaller data set, of course, but this is still, like, of course, has the same features, except by the our, you can see here at the end, we don't have the last, that is our, this one here, that is our target variable, because of course we want to predict that, so we don't have. So okay, so our next step then is looking to, so like by looking also into this data here, we can see another thing. There is like, if we pay a little bit of attention now, not only to the name of the columns, but actually into the content, we can see that, for example, here the state factor is something like state 1, 2, 4, and so on. Also, building class is something that is like a string. We already saw that before because it was an object. So you can see that those are all categorical variables, and categories in the sense that they are not like discrete values that we'll be addressing, as in like, for example, here, either as floats or as integers. They are like something that is going to be a category. But of course, like it's not because something is a number that has to be discrete. So it's also important to understand that, for example, year factor is a numerical variable, but is also a category if you want. So this is something they're going to be addressing soon. But yeah, so from that, like just looking to the data now, we can see that there are some categorical variables, like those here that I just mentioned, the year factor, state factor, building class, and facility type. There might be others, we might build others, and so on. So, but this is just an idea. So to continue looking a little bit further into the data set, we can now look into a little bit into the statistical aspects of the data set. So here we start with the training data set using the describe method. Here, I just made it a little bit like the other way around if you guys are a bit confused. Like here you have on the column the features, and you have here the statistical information. So you have here the count, then the mean, the standard deviation, minimum, max at the end, and then they got the division, got the kind of like the amount or the amount of counts that you have in each part of the data, like 25%, 50%, and so on. So interesting topic here that we will not address today, but we'll probably come back to this when we are talking about validation and so on. If we look into the train data set and we look into the year build, we see that this is again the mean and the standard deviation, if I'm not mistaken. Yeah. So here in the year build for the training data set, we have the year of 1952 and the standard deviation is 37 something. If we look now into the test data set, we see that the year build here, the mean is the 1963. This is a year, just so you guys like. I mean, this is still seeing like being calculated as a number and so on, like as a float, but it is a year. So like we see that the average of the year here is like the years in the training data set. Like the average of the year is much older than the ones in the test data set, and this might be a problem because the older buildings will have a different pattern of energy consumption than the new ones. And doesn't need to be a problem, but it's something that we have to bear in mind. And you might even consider like doing some different approaches for the data. But as like if you guys have time, this would be something that I would have a look into because it's quite interesting. That is like because we are always assuming that the training and the test data sets have the same distribution of all the features and so on. And I mean, the distribution might be the same, but the mean is not. And then this is something that is strongly correlated with our target variable that is like the consumption or electricity consumption in the buildings. So something important to bear in mind. But yeah, it's not a topic that we'll be addressing today. But just to give you an example, we have the 50% here. So 1, 2, 3 here. So we have like many younger buildings in the 50% of the data in the test data set, whereas here, Let me just find it here again. Here. So you see that here the 50% of the buildings are in the age of 19, were like built in 1951 on average, whereas the other ones were in 69. So this is like a 20 years or almost 20, like 19 years of difference, and this is actually quite a bit. So it is something that is at least a little bit something to consider having a look. Okay. So other than that, we have also our target variable. Our target variable is the site energy usage intensity. So it's basically the energy consumption or energy use in a location. And here we can also just like plot a histogram and see how it looks like. Here we can see that as we were showing the describe method with the describe method before, like the most of the buildings are around this value of 80. That is what we have here. So maybe it's not so easy to see, but it's like also like what we saw before. If you put like a ruler or something, you can see a bit better. But one interesting thing is that here, like we also don't have like a normal distribution. You can see that the data is a little bit skewed. And that's something that we can, we will have to pay a little bit of attention when we are dealing with missing values as well, like those variables that have missing values that we did not exclude. So, for example, if you take just the mean might not be the most representative because the mean would be a bit shifted towards the direction where the data is skewed. And then it would be interesting for us to, for example, look into median or some other approach for dealing with the missing values. Okay, so for features, now I'm going to mention like lots of notebooks. I borrowed some of the plots, but I put all the references here. You should be able to find them as well there. But just to have a look into the feature description, this notebook actually here has quite a nice description of the data. So I will not just like sit here and read everything because you guys can have a look as well. And some features are like quite self-explanatory in terms of names, but there are some of them that are not necessarily so obvious. So for example, we have the cooling degree days. So, sorry about that. So the cooling degree days. Then here is this is a cooling degree for a given day. Is the number of degrees where daily average temperature exceeds 65 degrees Fahrenheit. So each month is summed, and then we have like something like this per year for each of the locations. And this is like the same for some, what is the other variable that also had something like this? Yeah, also the heating degree days is going to be more or less the same thing, but of course like for heating now. So it's, there's something that is like a variable that you have to think a little bit about what it is and so on. But this is just good to know. So here we can also have a look into the variables, and maybe even like if you are struggling to understand something, then you can just come and think of what does actually mean and so on. So this is going to be important when we look into features in terms of like how they relate to each other and so on. So one first step that we can do in terms of looking into the features is looking a little bit more first at the features in isolation. And then after we just have like a quick look into like their distribution and so on, then we can go one step further and look how they relate to each other. So one initial step is to look into this, like that's what I mean by univariate analysis. That is like a look into the variables as in separate. So we can look first into the categorical variables, and just here like as an initial approach, as we mentioned before, like we have the variables that are just like strings, like that have like just a string, and then this is represented by the object data type. And then if we just look into those in our data set, for example, in the train data set, what are the variables that have this type, then we can assign this to a list, and then this is how we have our list of categorical variables. In the same way, we can do the same for everything that is not an object, meaning that is an integer or is a float, and this is going to be our numerical variables. So if you do this, then here, like apologies, doesn't look very nice, but then you can see that for the categorical variables, we have only those three, like the state and state factor, building class, and facility type. And then all the others are numerical variables. Of course, here we have to consider that this is actually not our numerical variable. This is our target variable. So of course, it shouldn't be along with the features. So we have to remove this as well from your list. So I think I'm doing this afterwards, if I'm not mistaken. Let's see. What else? We can have a look into the features, just like to see how their distribution looks like. So we can do this for this three initial categorical variables. So here is also like just a plot showing this, also just like another histogram showing how they look like. And then here it makes it like a bit clear like what we mean by categories. We can see that we have 11 apparently categories of state factor. And as a matter of fact, the state number 6 has quite a lot of values in comparison to the others. So this is something that when we talk about like dividing the features and so on, might be something that we have to bear in mind, that so that our model is not completely biased by this specific category from this variable. We can also look into the other variables, like we have the building class. Here is not as imbalanced. So here we can see that, for example, we have commercial and residential. Like, I mean, there is still, of course, I think around 25% of difference, but it's quite much less than here. So, but it's still like also imbalanced as well. So like we have many more residential buildings than commercial in our data set, at least in our training data set. That's what we are looking at here. And then the same if you look into the facility type. So the facility type is a quite interesting feature because, as you can see, and apologies that I know that it's not very easy to read, but it has quite a few categories. So this is something that probably when you look into feature engineering and so on, we probably are going to have to maybe cluster some of those categories together, see what makes sense, see what doesn't. But just an idea, this is not something that we're going to be doing today, but it's just like some food for thought if you guys want to, just like some ideas of what you can do. Like here you can see that the majority of the facility types, and facility types is like a building that has like some specific function. Here you see that the majority is like this multifamily uncategorized, and we also have the office uncategorized. So like apparently like the ones that we have the most are the ones that we don't know how to categorize. But it's important, like we have, of course, like also like a school, like educations and grocery and public assembly, like theaters and so on. So it is something that we can consider maybe putting something together, like that we have also like a police stations and so on. So we can try to think even in terms of a city. Of course, maybe this will require some domain knowledge, like research in terms to understand like what kind of buildings are we supposed to expect, more or less the same profile of consumption. Maybe educational buildings doesn't need to be only like where people have classes, can like classes as in school, but it can also be like some other kinds of classes as well, or things like that. So like this is something that is interesting to explore as well. Yeah, so here, just to make it a bit easier for you guys to read, we can just look into from this facility type, we just look into the ones that are unique. So we can see here just like the like we have 60 classes. And that's why I'm saying that is like, I mean, of course, we have quite a few data points, but still like 60 classes might be quite a bit, especially if you're like later on subdividing them again and again. So just something to bear in mind, because this can increase, like again, literally like double the size of our data set if you're going to be doing things like one hot encoding where you're having to divide all of this into zeros and ones. I'm going to come back to this in a moment. But it is just something to bear in mind that like here is probably where you're going to be spending some time looking to this data set, this facility type of the data set. Okay, then we have the year factor that we also agreed that is another categorical variable. This is a variable that is in terms of numbers, but is still a variable. This is still a categorical variable. So here you can see, this is also something that I borrowed from all the notebooks that I mentioned up there, that you can have like a look into how the different year factors. Here we have like from 1 to 6. And then we how it looks in the training data set and how it looks in the test data set. And then you also see that there's something funny here again, because the year factor, I think, is like this understanding that the energy consumption is growing across the decades and across the years as well. And then you have like a weight or something associated to it. And then if you can see that that kind of tells you exactly what we saw before, that the test data set has most of its data from much more recent than the training data set. And this is something that is like basically how you split your data. Like here we receive the data already split, and it's not very great because we don't have the target information for the test data. So we will have to figure that one out. There are many ways of dealing with this. One of them is just discarding the test data and just like do your own splitting with the training data, because we have enough data to afford that, and make sure that the sampling of the data that you're having is, for example, like distributed properly across all the variables that you have. So there is no tendency to just use some or other. And why I'm saying this is because, like, if you think about it, like if you train a model and you train a model on data that always has data on buildings that are old, and back then, like when the buildings were like from, I don't know, 50 years ago, people were using less energy, or like, I don't know, 70 years ago, people were using way less energy than we use now. And then your model will be always underestimating, or has the risk at least of being always underestimating the energy consumption because of this trait. Because you might not be able to catch it, like there's this difference in like, or there's this trend over the years and so on. So like we just have to be a bit careful. And then like the more fair way of dealing with that would be just like having a data set that you have like this range of years, and then you're just dividing it and so on. Like just picking like let's see, homogeneously throughout all the years that we have available in our data set. But just, yeah, something that is important to mention. If you look into our numerical variables now, like the ones that are not categorical, basically what we said, like everything else that is not categorical, that has like an integer or float value. Here we can just look into the distribution quickly. And here you can see like the floor area distribution. You can see the year built distribution. You can see that it started like I don't know, it's in the 1900s or 1900 something. I think 1900 maybe 20 or so, and until more or less 2000 somethings. Then you have the energy rating distribution and so on. So you can really like spend some time here, like also trying to understand a little bit this distribution. And you see that some informations have like some specific peaks and so on. So you have like more values that are distributed around some variables that are more distributed around some value. So that means that they don't have like a centralized distribution. This is something that it can be interesting to also know how you're going to deal with them. But yeah, this is also like a little bit of a topic of feature engineering, and especially the weather and the temperature variables are quite interesting because this I don't know if you guys are familiar with this, but like weather is a kind of a pain like to model and so on. So it's quite interesting to see. But you can see here like this is like the monthly variables, and then you have at the end. I'll just go quickly there. Also like those like more like weather, cooling, heating, and so on. But then this is just to have a look into how the distribution looks like, and then we can finally come into this point where we look into how the variables relate to each other. So until now we were only seeing like the distribution, or like I don't know, some like in the categorical variables, like more or less how they were, like the categories were distributed as well among the counts, but only for looking into one variable. Now we can look into like all of them together. This is not very easy to see, so apologies for that. Here is just an example of a heat map. There are many of those in the notebooks and so on. That you can pick your favorite color. I like blue a lot, so I like this one. And the idea here is to look into how the correlations among the features work. I'll try to make it a bit smaller. And apologies, I really hope you're not seeing this from your phone because it will not be fun. But let's try to go through this. So the idea here is that you have a correlation, like meaning as in like the higher the amount of a variable is, the higher is the other, or the lower is the one, the lower is the other. This is what you have when you have a darker blue here in this color scale. The lighter it is, the weaker it is the correlation, and like there is not much that they have to do with each other. Reason why we're doing that. Reason why we're doing that is because we have quite a lot of features, and as we saw like from the categorical features, we're gonna have way more. So we need to find a way to kind of filter out what is relevant and what isn't for us. And we found already some information about features that have quite a lot of missing values. But now we can have a look into features that are very similar to each other, because if they are very similar to each other, if we put both of them in the model, it's going to be a bit redundant because we are putting twice the information, kind of like a duplicate value, but it's even worse because it's a feature. So this is something that we can then use for doing this dimensionality reduction, if you want. So it's like, because then, I don't know if the temperature of something is very correlated to some other variable, we don't need to put both of them. We can drop one of them, and we should have more or less the same information. And of course, we should always drop the one that has like more missing values, because then we have more information for ourselves. So here we can do a quick look. Like this is more like a visual thing, but also from this notebook was very nice because there was some sort of automated thing. So for example, you can see here that try to go very to the bottom. Like everything that is on this column is the same thing that is here on the row. So our target variable is this one here, right? So is the energy usage and so on. So here, if you look, we are trying to look into something that looks a bit darker. Doesn't need to be black or super dark blue, because that would mean that it has like a one correlation that is like it's the same basically. But we can see like there are like lighter blues here, or like almost white here. So we can see that, for example, like there is a correlation between the floor area of a building and the energy consumption. And so it's the same for when it was built. And that's why we have to address the problem that we saw before about the age of the buildings. So for elevation, but for example, we can see that the energy star rating is a little bit weak, or weaker at least than those other variables. And then if you keep going, like in this is the second line here, and then maybe I'll try to make it actually bigger so it makes it easier for you guys to see. We can see here that, for example, the temperatures of February, the maximum temperature of February seems to be, this is the months of winter in the United States, seems to be more important, and also like in January, the maximum temperature seems to be more important than the minimum and the average. Meaning that if it's winter and the maximum temperature is some specific temperature, people might use less heating. And you have something similar for the months of summer. Here you can see that like all of this is a bit darker, because this is like a May and June and July. This is like the months that people use much more AC. So you can see that there is like some variables here are going to be more important than others in terms of those months. For example, here we see that the months of April and also like some parts of March are not so relevant, or at least not as relevant as the other ones. What we also have here, we can also see that these other variables here, for example, like the days of fog are not so important, whereas this the days with temperature below, especially this one here, days with temperatures are above 80 Fahrenheit are also more relevant. And this is all this thing like with heating and cooling and so on. So like whenever you have like a peak of temperatures, both like a not negative necessarily, but like a cold and warm temperatures, then you're going to be having people using more energies because of heating or because of cooling. So this is something important to bear in mind as well. And I mean, of course, here we are doing something that is very visual, but this is just like to have a feeling. This is something that, of course, like here we have a lot of features, so it's not so nice. Of course, you can try to like also make the same diagram with some smaller chunks of the data set, because you can also see like here I'm just looking to how they correlate to our target variable. But of course, they also correlate among themselves. And then if they correlate among themselves, we can see that there is going to be something that's the thing that I was saying about being redundant and so on. And this is our way to do this dimensionality reduction. So here we have information about just like some of those things that I was mentioning before, like just some of the correlations that were kind of like more obvious that we saw. But then this was all like a look into the data, having some first kind of like a glimpse and trying to understand a bit more. And now we are actually, now that we got this information, like we go to the other step that is like, what do we do with that? So we looked into some of the data, we look into the features, and then now we get more into action. That is like, let's start preparing the data for modeling. So that's the idea here. And this is the last part I'm going to show before I hand over to Aaron. Before I start, just want to check if there are any comments or questions so far. While I drink a little bit of my coffee. Let me check. Indu, you want to ask a question?
No, I'm good, Rosanna. Aaron was kind enough to answer the questions. Thank you.
Okay, good. So if there are no questions, then I'll just move on to this last part from my side, and then we'll go to the modeling. That is this preprocessing. So as I said, like I'm going to show like just some typical preprocessing steps that we follow in this kind of data that we have here. We have a little bit of categorical data with strings, a little bit of like a numerical data. But we are working on a problem that is like a predictive modeling. So there are like some typical steps that we follow. So some of those steps are like kind of like looking into things that can create noise to the model, right? So those things are, for example, if you have duplicate entries, by, for example, maybe by accident, someone put 2 times the same building, like, or a building that maybe has a different ID, but has exactly the same profile as the other for some reason. So this is going to be a bit redundant. And then as much as we have this for features, we also have this for like just rows, like just entries of the data. And then those should be things that we remove. I actually think in this data set we didn't have any. I don't know if I'm wrong, but it's just something that is like a standard procedure and is nice to do, and just like to be on the safe side. Other things that we will look into is like this dimensionality reduction that I mentioned before. That is like we have 60-something features plus some categorical features that will have also, I don't know how many other classes. So this can make your data set very complex very quickly. So we need to make sure that we are removing the information that does not add much to our, doesn't add much information to our models. And we'll be doing this, revisiting this heat map or these correlations that we just saw. And also we have those variables that we were talking about, that we can drop them because they have quite a lot of missing values. But there are those other variables that have some missing values, but we don't want to drop them because they actually bring relevant information for us. And but we need to make a decision of how we're going to be dealing with them. So then after that, we have to, of course, like still think of like how we're going to scale the data, and also like the encoding of those categorical variables. So like let's just get started with that. For dropping the duplicates is quite simple. You can just use this drop duplicates a method. If you use in place, that means that you're already applying this directly in the data set. And then you don't need to assign it to another variable. You can just do this directly. But of course, if you prefer to, like, I don't know, be careful and so on, because this is actually a good thing to do, you can try to use false and then just assign it to another variable. And then your train data frame is going to remain the same. So that's one step. We also have the dimensionality reduction. Here, I'm actually following these steps from this very nice notebook. That is the same one that had the heat map. So here, the idea is to just look into some threshold. So the idea is like we are trying to look for features that are very similar to each other. And but the value of the correlation can be from 0 to 1 here. Like there are other kinds of correlations, but the ones that we are looking here are from 0 to 1. We also have like the ones that are negative correlations. Then you have like also like anti-correlation and so on. But here we are looking to this kind of correlations from 0 to 1. So if it's the closer it is to 1, the most similar the features are. The closer it is to 0, they have nothing to do with each other. So here we are putting a threshold of 0.95 to this correlation. So it will catch everything that has a correlation that is between 0.95 and 1. Basically, that's the idea. And here we can see that there are quite a few of those variables, like they are coming in pairs. So here you can see that the average temperature of January is correlated to the minimal temperature of January, which is not necessarily a surprise. I mean, of course, it's not something that has to be always very obvious, but it is something that is there. We also have a maximum wind speed correlated to the direction of the maximum wind speed, which makes a lot of sense. However, those variables here are not so important for us because we already decided that we're going to be dropping them because they are having too many missing values. So we have also like cooling degree days with the average temperature of August, and so on and so forth. Like here you have another variable. There is all the other variables that are also not so relevant for us. So basically, the ones that are relevant for us is this first one here about the January temperatures, and also the ones about the cooling degrees and the temperature in August. So here we can decide, I will not do this, but we can decide which one we can still keep all of them, but the idea is to look into like if they are really, really correlated, it doesn't really add much information to the model. Some of them might have like more missing values than the other one, and then we just keep the one that has the least missing values. So that's the idea. And so if you want to look into how to remove those missing values from the variables that we're keeping. I'm going to show very soon like how to deal with this here. But if you want to, like there are the variables, for example, the year and so on that we were like that had like some missing values, and we have to keep them. So like we have to keep those variables. So like how we deal with the missing values. If you remember, we saw that the distribution is not exactly a Gaussian or a normal distribution, meaning that the values are not homogeneously distributed across like the histogram. And that means that basically if you take like the mean and the median are not going to have the same value. So the median is going to be more like shifted towards the peak of the distribution, whereas the mean is going to be just something there in the middle. Actually, it's the other way around. But so the important thing is that we need to here, because we don't have this distribution that is a Gaussian distribution where both those variables would be the same. It makes more sense for us to take the median, because then you're going to be having more information about like a following this shape of our distribution. So here is a way to address that. So for example, we have the feature. Here we're just like going through the features from the numerical features. And then obviously we're going to be only putting the median values there if we are dealing with numerical features, so that's why. And then we're going to be, we just decide what is the imputing methodology that we're going to be using. Here we are just saying that we are using the median. You can use something else. You can use the mean, or you can use 0. You can use, I don't know, drop and so on, but just something that is important. And then you just have to make sure an important step is that you have to like to fill those numbers with this value, and you have to do this both for the training and the test data set, because if you, the moment you change something in your training data set, you have to do something that is consistent with the test data set. Otherwise, you're changing completely your training data set. You're training or modeling something, making the assumption that the test data set will have more or less the same distribution, will look more or less the same, will have more or less the same scale, and will not, and then it will not make any sense. So we have to make sure that we are doing this for both. So yeah, so that's the step for like imputing the missing values. And then if you want to like come back to those values that we thought, like those variables that we thought that are not so relevant, then you can decide which variables you want to drop. So here we saw that those 4 here, those 5 here, sorry, like those 4 that have the missing values plus the ID, we are going to drop. If you want to drop one of those that we already saw that have strong correlations, you can also do that. You just like at least how I'm doing it here, like you can just like create a list of the things that you want to drop, and then you just go through the list that you want to drop, the features that are in the list, and then you just remove them from the list of numerical variables, or for the list of categorical variables, or for the list of columns in your data set, and so on. So this way you can update your train and test data set. Here you see that I'm calling them now preprocessed, meaning that now we already dealt with the missing values and also with the features. So here is like what we have now. So we dropped those here in the list. Here you can see that I saved it for different name intentionally, because you see that there's going to be a lot of back and forth of what you have to drop or what you have to do different things. So if you make a copy here instead of like just doing this in place, then every time you're going to be running something, you're going to have to run all your notebook all again. So here is a good moment to actually make an in place false, and you just say, I mean, this is a default. I just wanted to make the point. You don't even need to put if it's false. So, but just like so we have all in the same place. Then after that, here, like we dealt with the missing values. We already addressed like the features that we want to get rid of, like with this dimensionality reduction, like this first approach of the dimensionality reduction. And then now we can go into the feature scaling. That is like looking how we want to rescale all the variables that we have. Here again, like we have variables that have different ranges and so on, and we don't want to make the model understand that different ranges, like that a number that is bigger necessarily means that it is like it has a bigger value than some other variable just because the range of the variable is smaller. So you do this by rescaling the model. Rescaling the model, you would just keep the distribution and so on, or you can change the distribution to make it like a more Gaussian and so on. So this is what we are doing here. And again, we have to do everything that we do for a training, you have to do for a test. So here again, we are using standard scaler. There are other kinds of scaling that you can explore, and I actually recommend you to explore, because again, this data set is not exactly a normal distribution. So there might be other scaling that you might consider using. This is something that I would recommend to also have a look. Here is another another article that you can have a look that explains a little bit more about it. Let me just copy here in the chat. This one has is one of those paid ones, so you have to go to this private tab so you can actually see it. But if you do that, then you can actually see it, and that's quite nice. And has some explanation about other scaling. For example, there is this min-max scaling. There is some others as well that might be more suitable for the data distribution that you have. That would mean that you might have to have a closer look into the distribution that you have for all the features that you have in your model. And this is, of course, like all the 60-something. So this is like quite a bit of work, but it's something that is quite nice to also like make sure that you have like a proper like analysis and so on. So here we are again just like applying this transformation, like we are defining that the scalar that we are using is this one. If you want to use another one, you just have to change that. And then you are fitting it. Important thing, we are fitting it to the training data set, and then we are transforming both the training and the test data set. But the test data set is being transformed with the fit that was done for the training, just to emphasize that. So this isn't something important for us to understand. So now we have to then, this is just an example of, for another example of a scaling that you can use as well. And then our last step now is to encode the categorical variables. So the categorical variables we have here have both, if you remember, like we have numerical ones, like this, how was that called? Like a state factor. There is like a number and so on. And we also have the numerical, the string ones, like the facility type and so on, that are like if you remember, like police stations and schools and so on. So like this is something that for doing that, like again, this is another step that there are many ways of doing that. One thing that I think is interesting here is to use one hot encoding. One hot encoding means that if you have like one variable that is like time of the day, let's say morning, afternoon, and night, instead of having like those like as morning, afternoon, and night as a row, as a column, sorry, of your variable, then what you have, like you transform this morning into a variable, and then you assign a number that is 1 or 0. So if it's afternoon, it's not morning, and then morning will be 0, and afternoon will be 1, and night will be 0 as well. So that's more or less the idea. And this is what you're doing here. You can just ignore this part here because this is actually not what I'm using. There is another nice reading about one hot encoding. Let me just put it here. I deleted the wrong file. But here is basically like a simple way for you to do that. You just use with your pandas data frame, and you define what columns you want to transform into this style of categorization. And here we have our categorical features that we already defined before. As you remember, this was a list. So here we are passing a list to this method. And then we have here at the end, like just like a showing after it is encoded. So here we changed the name again. So we took the pre-processed data set for, this is wrong, sorry about that. This is test. but we took for both of them, and then we get the modified one. So here, for example, just for the trainee, that is the one that I did right. You can see that before we had a state factor, just the variable state factor, and then you would have 0, 1, 2, blah, blah, blah. Now you have state factor underscore 0, state factor underscore 1, and so on and so on. And then here you can see that the ones that are 1 are not 0 and vice versa, and as they should not be. There are some cases that this is actually something that can be possible, but that's not really the case here. So this is one possible way of doing coding. What that means that if you have 60 features here, or 60 categories for your feature, they are all those 60 categories are now becoming new features. And that means that's exactly what I was saying before, that now you are transforming, you're basically doubling the size of your data set in terms of, not the size of the data set, but the size of the features, the amount of features that you have in your data set. So this is just something that I wanted to show. I was just looking to defining what are the final categories now. And you just have to take the difference of like what you have in terms of numerical features. And just like remove the numerical features now from the columns that you had, and then you have like all the features that you have now in the data set. But this is like the last part I wanted to show you, and I think now I will pass over to Aaron, so we can continue with the last part that is like now exploring a little bit of like how we can with this data set, like we already, after all these pre-processing steps and after understanding a little bit of the data, how we can go ahead and start some training and making the submissions and so on. So let me just stop sharing. Okay, so Aaron.
Thank you. Yeah.
Ready to go.
Thank you, Rosanna, for such an amazing session. So I am just going to start with model. So first of all, we'll have, let me explain you. I'm just going to the basic of machine learning model, assuming like, what models are and how we are going to implement them, right? So we'll quickly pass through, yeah. So whenever we apply any kind of machine learning model, either it's deep learning, supervised learning, whatever the model is, we has to, pass through these steps. So you always have something to input to train, and then you got output. So whether it's, supervised learning, reinforcement learning, deep learning, whatever the model type is, you you follow these steps. Like first of all, you should have data set in your hand, and then you apply some model on that, and based on those models execution you got some results. So that's actually machine learning process. So when we say we have machine learning algorithm, we have supervised learning model, unsupervised learning model, and reinforcement learning. For supervised learning model, we normally already know which kind of results we want. That's what we are going to apply today. So I'm not going unsupervised learning and reinforcement learning in today's session. Maybe in future session we'll go through them as well. So example of supervised learning model is, for example, uh, we have certain emails and we want to categorize whether the email is spam or not. So we have 4 emails. From these 4, first one is spam and rest of the 3 are not spam. So to define whether the mail is spam or not, we always have certain features. So we might have feature like the email is new to you, you don't have connection with the person who is sending you, the email is not from any institution, the email identifier name is starting with number, not with the person or any you can say individual. So it could be spam. So there are many features which are defining like email is spam or not. So based on that knowledge, our algorithm learns those feature, and then in future algorithm predicts whether it's spam or not. And most of us are already familiar with that. Our uncategorized email always go to spam folder, although sometimes that email used to be important, but the person is sending it for the first time, so that's why it goes to a spam folder, right? So today we are going to apply, like, there are many machine learning models, but we have just few models to implement and see what are their results before going to into deep learning or other application of models. So we'll go with linear regression, k nearest neighbor, decision tree, random forest, and XGBoost. Before applying that, let's have just a quick, you can say, brushing up our knowledge. What are these algorithms and why we are using them? So for linear regression model, we always have a linear line, and on both side we have data points, along with that the line of regression. So that's how linear model works. Then we have k nearest neighbor. So in k nearest neighbor, we normally classify similar kind of objects all together, uh, which have uh, the less distance. So for example, you see in this image we have different representation of you can say dots, squares, fill squared, and something like that. So we have divided them in three different you can say clusters, and we are mapping them for we are saying, like, with certain different make couple up those elements. For example, these elements are coupled up, and this is also coupled with this one because that has a less distance as compared to this one, right? So coupling this is not making sense for the algorithm because we are using the algorithm joining the points which are more nearer to each other, right? And then we have decision tree. In decision tree, we normally on top of at top we have our problem, and then we have certain situations, like we will see what is situation outside. Is it rainy, overcast, or rain? So if it's sunny, then we'll check whether there is humidity or not. If humidity is high, then no chances of rain, and normal there are chances of rain. Overcast mean yes, there will be rain. And if outlook seem like there is a rain, and then we'll test the condition of wind. If wind is strong, no, there will not, the chances of rain is less. And if it's weak, chances are more. So it's something like you have on top, you have certain scenario, along with that certain possibilities, and based on those possibilities our algorithm make decision. So that's how decision tree works. Then we have random forest. So in random forest works exactly like uh, our decision tree, but we have multiple trees over here. For example, we have tree 1, tree 2, and tree 3, and based upon these results, majority voting or approximate value is selected and make the decision based on certain class. For example, from the previous class, we figured out there will be rain, and then we have three trees. This says yes, rain, and this says no. Then random forest pick yes because two trees are returning same result. So that's how random forest works. Then we have XGBoost. So XGBoost is most popular machine learning algorithm, although it comes under most of the time in deep learning, but I have included over here because I found a good, uh, you know, Kaggle code on that, so that's why I included over here. Regardless type of prediction task in hand, either it's regression or classification, it's work really well. So we have different boxes over here. We have box 1, box 2, box 3, and box 4. In next slide I have explained how these box work. So in box 1 is actually classifier, usually a decision tree or decision stem, creates a vertical line split data 1. It says anything to the left of t1 is plus and anything to the right of t1 is negative, like or minus sign. However, this classify misclassifies the 3 point. What are the 3 points? So basically we have plus point and minus point, and these three are misclassified using in the box one, or we can say method one or division one in using this. Similarly, we have over here we are saying uh, left box is for plus and right is for minus, and 3 points over here again are misclassified. They should be in this box but they are not, unfortunately. Over here we are saying like the top and bottom, and over here we are dividing our box in a way that we try to make the division in a way like every single unique value is being inserted in its appropriate box. That's the visual representation of this XGBoost. Any question up till now? All right, I can't see any question. Okay, let's move now. Now we know how these models are working, and as we have been discussing earlier as well, the major task is data cleaning, data engineering, and pre-processing. Model building is just you need your data point and apply those algorithms. So we can we I always explain that we can apply model just in 3 lines of code, and I'm not just uh, you know overrating the statement. That's the truth. You just import certain classifier, you fit the model, and you predict the result. These are just 3 lines of code that is sufficient to apply any kind of model. So I have called linear regression, k-near neighbors regression. Tree ensemble is actually random forest because it's joining many trees, and XGBoost. So these are the libraries I am calling, and over here I have created a simple, you can say, array, and I am adding value of each model over here. Like whatever the result are from linear regression is going to saved in the model, because I need result of these model, right? So over here I am implementing actually models and storing them uh, in an array, in a list, right? So I call them, I append them, save the result in the array, and over here. Okay, now let me show you what does mean by k-fold, and then we'll come over here. Any question up till now? So over here we have called the model and deployed it and saved it in a list, right?
Hey, Aaron,
Yes,
I
please.
just have a question. I know we did a lot of pre-processing with Rosanna. Now, for the different models, do we use the same data set, or do we need to pre-process it differently for different models? Because my understanding is that different models have their own advantages and disadvantages when it comes to the data set.
Yeah, exactly. So when it comes to the data set, different models have different advantages and different disadvantages and advantages. I totally agree with you. But we can use same data set, and that the data set is the similar one on which Rosanna has shown pre-processing, and we have implemented model on that data set like our model. Sometimes there are the feature like the special value transformation required for the model, but pre-processing does not affect the model. Like there is no specific requirement for the model, like this kind of feature should be there. Yeah, there are some models who which require certain type of values or transformation in terms of, as we discussed previously, integer 64, then floating point and something like that. Other than that, there is no like harm taking similar values and applying different models.
Great, thanks.
Rosanna,
just,
you want to?
I just wanted to add a comment. There's also something that I didn't know for some time, like that for this scaling that we were showing, like scaling normalization, for tree-based models, they are not always necessary. But for example, whenever you're going for deep learning or neural networks and so on, then or regression as well, it is required. So, but of course, like if you have it won't hurt your model to have like the scaling. It's just that it's not necessary. Just wanted to add this comment.
Oh, thanks. Just can I clarify another thing here? Because we talked about categorical scaling, the categorical ones. Sorry, not the categorical, the numerical ones. And I'm just trying to get an understanding as to whether based on each feature we can use different scaling methods, or if we choose one, then it has to be applied uniformly across all the, the features that we are scaling.
You mean that if the feature, the scaling that you're using has to be the same for all the features?
Yeah.
Okay. I don't know if you want to answer that.
Yeah. So, when normally when we use the models, so models are what we can say a pre-trained or predefined algorithms, right? So to get uniform result, it is always required, like we should have a similar scale for every single feature. Otherwise, sometime model ignores that, it doesn't send back you an error, but that makes difficult for you to understand like what unit is over there. So even we are using integer value with different transformation, we got some different result because of the memory usage and representation issues. So it is always recommended like there should be uniformity in the scaling of every feature as much as we can, but it's not 100% required for every single model.
Got it. Thanks, Sarah.
Yeah, welcome. And as Rosanna just shared, for normal model, it doesn't through you any error. But when you work with deep learning, like when you create neurons or some tensors, then everything should be on same scale.
Good. Thank you.
All right. Any other questions, or you want to share something from your side? Okay, so we have been using k-fold at various places, and you must heard as well. So k-fold is actually a cross validation, or cross validation is actually a resampling produced used to evaluate machine learning models. So whenever we use cross validation or validation, it means we are validating our model, like whatever our model is producing, either it's working fine or it's just highest number in returning the values. As you see in our model, like when we see our model, when I see it's making a data points, and the result of box 1 maybe is 99%, but it has 3 wrong predictions, right? That we can only see through visualization. With computation we might not able to identify like these 3 points are misclassified. So validation is done with multiple techniques, so that we make sure whatever the model is we using are classifying different data points rightly or accurately or not. So that's why we use, and there are so many methods and there are so many techniques based upon different kind of algorithm, different kind of data sets. uh, we have different method of validations, and k-fold is one of them, to actually validate our model. And its process is actually you shuffle it automatically shuffle the data normally. split the data set into k groups, and k is defined. We always have a k. For example, when we say k is 10, so it makes 10 different groups randomly from that data set. For each unique group, take the group as a holdout or test data set, take the remaining group as training data set. So it like, for training and testing, it automatically shuffle the values. It's only like it doesn't shuffle the values in training data set, but it also takes value from test data set also. Fit model on the training evaluation data set, retain the evaluation score and discard the model. Summarizes the skill of the model using the sample model evaluated score. So that is actually the true, what we can say, performance of model, what we do using, uh, validation method. Now let's come back to this. Any question on k-fold or validation? Okay, so there is no question. Let's move forward. So over here we have imported, library k-folds from Skyline library, and then cross validation score. Call is equal to algorithm, mean square, and standard deviation, uh, mean square error. So these are the column we have created, right? And we create a data frame from that. That's a simple, you can say, what we can say, simple script to write to create column and data frame. Then we are using for name model in the models. This one we are calling these models, like for every single model it will call it, and that's just a print statement. It will apply a fold with 5 splits, not 10 splits. And random state is 10. Random state, we normally define random state just to make sure like there is no replication value. So we can normally we use 42. We can use any number between 0 to 99 or something like that. And then we are actually from cross validation score that is applied on train dataset, and like where at from train dataset it has also excluded the value of you know uh, our feature where we have applied the model, right? And again, since we have 5 folding, so we have 5 folding over here, and then we are storing the result over here, right? So this whole, what we can say, within this loop we are applying our validations using k-fold method and then storing our result. It is showing us result. If you see, we have this printing statement, this print statement. It will print the statement like it will fit the model one by one. First it will fit the model, linear regression, and apply k-fold, and then it will fit the model on k nearest neighbor and apply the fold unless until it go to XGBoost, right? And then it will print the result sorted by the highest value first. So we have random forest on top, then we have XGBoost, then we have k nearest neighbor, and then we have decision tree, and linear regression is at bottom. So using this method, whatever Rosanna has shared with you, with this feature engineering, we find out like random forest is working better. Now we know our model accuracy is around 53%, so we can pick up this model and start working on feature engineering more, so that we would able to increase accuracy of this model. That's the one thing. The other thing is that because we have applied simple classification model, we have not gone to deep learning or transfer learning or some uh, other methods. So let's take the similar data set and try other methods, because we have seen like these model, like accuracy of these model is not highest using this feature engineering, right? And then once we figure out like the random forest has the highest accuracy. Now we can apply that. So we have model random forest regression that we have already called out over here, right? And then we need to apply that on train and test data set and then predict the result. So these are the three lines I was telling you. We can apply any machine learning model using three lines of code, like importing it, storing, calling that what we can say model, and then applying that model. So this is model.fit. So if I write over here something, maybe this could be anything, first model. So then I might write need to write over here first model, right? Dot fit, and then add train and test value, right? And if I want to predict what are the results, I need to write predict. That could be anything. That's only your variable. So it can be prediction is equal to rf dot predict, and we always predict on test data set, not on train data set, right? So we can predict that, and then we need to submit this file. So if you have to submit that, you already know, for submission we need to write site underscore EUI. ID is already there, and what is equivalent to this value is equivalent to this prediction, right? So over here I need to write prediction, and then our test submission will become ID along with its site prediction, right? And then we can convert this file into CSV. And how to convert that data frame into CSV? The method is whatever the name of this data frame is, dot to underscore CSV, and then whatever you want to give it as a name, you can say my final or whatever you want to give or assign a name, or you are asked to write it just like submission.csv. And we are saying index is equal to false, like we don't have any index over there, right? Otherwise it will automatically create 0 1 2 3 something so on. So we don't need to write any index over here, and it will show you result, right? Then I have already added over here root mean square error, and that is actually required, that is required for us to submit. So root mean square error is how, like, your data point is further from this actual point, sorry, this linear line. So the more further it will be, that is considered like it's not considered a good value. So mean there should be like based on thumb of rule, it is considered like between 0.2 to 0.5 is considered a considerable a good distance of the point between this line, right? So these are the pointive line, and these are actually residual. So if you define it, its root mean square is the standard deviation of residual predicted error, and residuals are the measure how far from the regression line the data points are, right? So the more far these are not considered good, right? So the less closer these are, it means they are highly correlated and they are affecting each other. So that's it from my side. If you have any question, you are more than welcome. Yes, please. You can unmute yourself and you can.
Hi, Hiram. Are you going to go over the hyperparameter tuning and all that next time, or?
So I deliberately haven't added over here because I was expecting like we might not have much time over here, because I was expecting there may be more questions. regarding implementation of these. So that's why I haven't added that. So
No
definitely
worries.
we'll do. Yeah.
Okay.
We'll definitely cover in next session. Yeah.
Thank you.
Welcome.
Thank you, Aaron.
Thank you. Anyone else? If you have any question.
I just wanted to say thank you to both you and Dr. Rosanna. It was really, really helpful. I mean, you guys explained it very, very well. Like the basics are so important. So I think it was a great session. Thank you both.
You're welcome. Yeah, you know that's what I always focus on. Just try to understand what you are doing instead of going into deeper like something where you stuck. And most of the time focus on feature engineering. So probably in in every week we'll build up something on feature engineering, and then we'll move forward with few of the models.
Yeah, and I think it's nice that we are trying to follow like some structure of like having something ready for submission. Like, I mean, there are already many notebooks that you guys can also follow. This, what we are showing you is also actually like a kind of like a summary of all the notebooks. And so because the idea is that it's going to be a lot of back and forth. You'll see that it's never linear, like you build a model with this preprocessing or with these features and now done, like it's not only about looking as Aaron just said, like very well, like it's not only about looking to the tuning of the models. They are also important, of course, but understanding like the features. For example, in this project here, we have like, it was the same case in last year with a completely different data set, but we do have a lot of features. We do have a lot of information, and it's always tricky to, that's the beauty of data science, like it's always tricky to detangle all of this information, so what is relevant, what isn't, and like to make this decision of like how you deal with the data. And then because sometimes you can have like a very fancy model and so on, but you can only learn so much because of the data. So that's a very good point that Aaron mentioned.
I have a question on, do we have time? Can I ask Rosanna on the, because you are going through the, how we impute the missing values. Is this a good time to ask, or I just wanted
Sure,
to...
yeah.
Okay.
Of course.
I was wondering, like, this is more I want to experiment with, because it's like temperature, like instead of median, can be used like nearest neighbors, the KNN way of imputing it. Would it be more closer? For example, if today is cooler, most probably not that it follows that way, but could we use the nearest?
let me just turn on my camera so you can see me. In principle, yes. You just have to be a bit careful because of the. I agree that of course, if it's today is I don't know, some temperature, it won't probably, hopefully, change like, I don't know, 50 degrees on one day and so on. But for that, I don't know if I understood your question correctly, but for that would have to have information about the past, like information with time. And we don't have this here. So,
Okay.
I mean, of course, you can still cluster like other features and see if you find some information, but maybe more like for feature engineering, I would say, like to understand how to put them together. But I don't know what do you have to say about this, Aaron?
Yeah, I think that made sense, Roseanne. I forgot that we don't have like every day. It's more like January. Okay, yes. I have to look more carefully at the data. Yes.
But there might be some correlation if like the average temperature of the month before. So that's because although we don't have, it's actually a very good point. Although we don't have timestamps or something like that, January, February, March, and so on. Like, I mean, they are not like just like features, right? Like they have some sequential order between them, and cyclic as well. Like so for like if you give this data set to, I don't know, to an alien that doesn't understand anything about like human calendars, they will not understand that there is like that after December comes January again, So like we might, for example, like do some feature engineering on this regard, like of maybe like putting, for example, creating even new features like what is the average temperature of the month before, I mean, which we already have and so on, but it's just a way to see that more like in the perspective that you're saying.
Thank you. That helps. Thank you.
All right, so we'll